So today we'll be going over some mass transfer problems. I figured that actually seeing some of these problems being solved in real time might be more useful than just going over the theory. And so in the last video, we basically covered, like a Cartesian coordinate steady state problem. And so in this one, I'm hoping to tackle, sort of the other coordinate systems, because in real life you might not see Cartesian coordinate systems. You might see cylindrical systems. That's common with pipes, as we'll see for this problem, and spherical coordinate systems as well, for maybe like some sort of solute that's dissolving in a tank. And so we'll see that, and then we're going to tackle unsteady state problems as well, so you can see kind of a glimpse into how that might look. But first, let's go over this problem right here. And so the problem is basically asking us, okay, find the steady state. So assumptions, right? We always want to make sure that we know what our assumptions are. So our assumptions are, first of all, the problem already says steady state. All right. So we need to find the steady state concentration profile and flux. So what do we want? The problem says, or actually we should say this is our goal. So goal, calculate the concentration profile, right? So that's one of them, and also the flux, right? So we want to know the concentration profile and the flux. All right, so continuing on, we want to find the steady state concentration profile and the flux out of a pipe, right? So it's a pipe. That tells us that most likely it might be cylindrical, right? Pipes are usually cylinders. The pipe has an inner radius r sub I and an outer radius r sub O. The solute has a fixed finite concentration C1I inside of the pipe, and is essentially at zero concentration outside. And so as a result, solute diffuses through the wall with a diffusion coefficient D. All right, so we know that there's a certain diffusion coefficient D, and we're kind of given, that there's a concentration inside, but it's basically zero outside. So what does this tell us? This tells us the boundary conditions. All right, so that's another point. Let's get our boundary conditions down. So boundary conditions. Right? So boundary conditions would be looking at this. They would be concentration 1. So we're going to call this the species 1. So I'm going to denote all the concentrations 1. You'll see why this is important as we get to problems that might have, two species moving at once. So you want to be able to keep track. So C1, right, the concentration of species 1 of the solute at R equals R sub I, right? So that's the inside. That is equivalent to, it's given in the problem, C1I. So we can see that right here, right? And then our second boundary condition is C sub 1, right? At R equals the outer radius, R naught. That's equivalent to 0, right? Because we have essentially 0 concentration outside. Perfect. So now we have our assumptions, we have our boundary conditions, and we have our goal. Now we can get started with the differential equation. And so you might remember that last time we kind of derived fixed second law, it's called sometimes. And what that tells us is how is the concentration changing over time. And so we're going to use that in order to get our differential equation. So we have Fick's law, right? So let me go over here. Fick's second law, which is essentially derived from a mass balance. So if you want to derive it with a straight up mass balance, feel free. But I will go ahead and skip on over. And so what Fick's second law basically says is that the concentration, right, over time, which is basically the accumulation, right, del C1 over del T, is equivalent to the diffusion coefficient D, right, times the second partial derivative, right? In this case, it would not be a partial derivative, but because we're dealing with only one direction, but you'll see that it's really important. And so in this one, typically, you'll see that I'll write it down. Fixed second law is basically, let's say that it's in the Cartesian coordinate system, right? So this is what you're used to seeing, right? But I already said that this is probably going to be the cylindrical coordinate system. And so what you want to do is look at the Laplacian, right? So the Laplacian, right, for cylindrical coordinates, what is that? Well, that would be nothing but 1 over r, right? d dr, r times d by dr, right? Plus 1 over r squared, 1 over r squared times d squared d phi squared, right? Plus d squared over dz squared. So if you look up the Laplacian, you're not expected to know this, but if you look up the Laplacian for the cylindrical, this is what it is. And you want to know the Laplacian because essentially this is Cartesian, right? But we're not going to be using the z-axis, the z-axis for the diffusion. As you can go back to the problem, you can see that the solute is diffusing through the wall of the pipe, right? So if I was to draw the pipe itself, it would look something like this. So we have this, and kind of, right, we have, let's say that we have the solute in the center. It's diffusing out like this, right? And so if it's diffusing through the walls of the pipe, you could say that, this would be the z direction, right? That's the z direction. But it's not moving in the z direction, it's moving out in the r direction. And so what that means is that we have to use the cylindrical system. So this is the Laplacian if it was Cartesian, but we're going to have to use this since it's cylindrical. Perfect. So our next step is now, this looks really complicated, right? Well, as I said before, there's kind of some assumptions we can make as we go back here, right, to our assumptions. I think when I said that it was cylindrical, it's also important to note it's only in radial direction that we're having transport, right? So what does that mean for our Laplacian? That means that we can basically cancel out all the terms that show movement in the phi direction or the z direction. So these are 0, right? No diffusion going on in the phi direction, which would be essentially the phi direction would be kind of like, or you can call it the theta direction. It would be like this, right? There's no diffusion. It's also symmetrical, so you don't see any movement in that. And so what that means is now we can rewrite fixed second law for our problem statement, right? Another thing is that this is steady state, right? Things are not accumulating. This term goes to 0. And so we can rewrite this, right, as this. So now we can rewrite fixed second law as 1 over r d dr times r, and I'll plug in our function is essentially the concentration, right? So I'll plug that in, dr, right? And that equals 0. So that's our fixed law, essentially. And just going back, what we did was we realized that this is steady state, so this term goes to 0. This actually, this second derivative is for a Cartesian coordinate system, but what we did was we basically took this. I should do this in a different color. We took this and we kind of swapped it out since we knew that this is the correct system. So essentially, whenever you see spherical or cylindrical systems, you're going to want to identify which direction the mass is moving in, and use that derivative in order to calculate the mass transfer. And so this is how we got this equation. Perfect. So now all that's left is to start solving this. This one basically goes to 0, right? Let's imagine that we multiply both sides by r. That one goes away. And so what we can do is that we can take the integral now. So we can take the integral of both sides, right? We take the integral of both sides. What do we get? We get r dc1 by dr is equivalent to some constant a, right? Because when you take the integral of 0, you get some constant. Perfect. And so now we're going to divide both sides by r. You get dc1, right? dc1 by dr equals a divided by r. You can take the derivative of this too. The integral of this too. And what you get is c1 is equivalent to a ln r plus b. If you want to, you could have just multiplied both sides by kind of dr and then, done that. But this is what you get. You get the two constants, a ln r plus b. All right, so this is where now all that's left to do is now that we have the general solution, we want to plug in our boundary conditions and, solve for the constants. So boundary condition 1, right? What was our boundary condition 1 if we scroll back here? It was that C1 at R equals the inner radius is C1 I. But yeah, so BC1 is C1 at R sub I is C1I. But in order to solve for the constants, it's always easier when you have a homogeneous boundary condition. What does homogeneous mean? It's when one of the boundary conditions equals 0. Because what that means is now you can kind of eliminate a whole term. And so it might be more useful in this case to apply boundary condition 2, which is C1 at R, the bigger outer radius, is 0. So if we plug this in, right, what do we get? We get essentially 0 equals a ln r naught plus b, right? So that means b equals negative a ln r0, r naught, right? And let me also plug in this one. So if we get c1i equals a ln ri plus b. Okay, so now that we know these two equations, we can kind of, plug in what b is into this equation and start solving, right? So let's go ahead and do that. So now that we know what b is, I'll go ahead and plug b into this equation and we'll see what we get. And what we end up getting is a ln of ri minus actually should be bracket ln of r naught equals c1i, right? And so if you solve for this, what you get is a equals c1i divided by ln of ri r naught. So now that you have that, it's pretty much simple to solve for b using this equation up here. You get negative c1i ln of r naught, all of that divided by same denominator. Perfect. And so our problem, going back to our problem statement, what did we want? We wanted to find the concentration profile and the flux. And so now that we have our two constants, we can, plug them into the original general solution over here, and we can get what the concentration profile is. So let's go ahead and do that. So C1, right, is a function of R, and that equals C1i ln of R by R naught divided by ln of Ri R naught. And you might be asking, okay, well, we kind of skip some steps over here, because we have this plus this. But essentially what I did was I recognized that when you take when you divide two things inside of a natural log, it's the subtraction of that, and we're basically multiplying it by ln of r here. And so when you multiply two ln's, it's the product. And so if you work this out, you'll realize that it looks something like this. Perfect. So now that we have our concentration profile, what was the other thing that we needed? We needed the flux. So how do we get flux from concentration profile? Well, you might remember that flux is defined, right? Flux is flux flux is nothing but the mass per unit area per unit time, right? That's what it's defined as. We kind of already have mass per volume, right? That's what concentration is. And so in order to get from a concentration profile to flux, you can think back and see if there's any formulas that we can use, right, that relate concentration to flux. And you might realize that Fick's first law, right, Fick's first law, which is J is equivalent to minus D dc1 by d, in this case it would be dr. This actually shows a relationship between concentration and flux. And so it would be useful for us to apply the Fick's first law, onto this in order to get that. And so if we take the derivative of the concentration profile, what you get is J1 equals minus D times C1I divided by ln of Ri by R naught times 1 over R, right? Because the ln of R is derivative of that is 1 over R. And so this is now your flux, right? We've solved for the concentration profile, and we've solved for the flux. Concentration profile and flux. And so that's how you would do something if it was steady state for maybe like in this case it was cylindrical, but if you were to do spherical as well, you would just, the only thing different that we do now here is that we include a different derivative because you have to include the Laplacian. But everything else is still the same. You write your assumptions down, figure out which direction the diffusion is happening in, cancel out all the other terms. If it's steady state, you can cancel out the dc by dt because it's not changing with time. Figure out your boundary conditions, get the general solution, and then just plug in the boundary conditions for the constants. You get a concentration profile. Once you have a concentration profile, since the problem states that it's only diffusion going on, then you use Fick's law in order to get the flux. That's all the steps you need to solve any steady state diffusion only problem. Perfect. So now you might be thinking, okay, well, the problem is going to get much harder if we have a non-steady state problem, right? Let's say that we have a problem where now it's changing with time, right? So you might imagine that if it changes with time, you're going to need to have more boundary conditions, right? Because you have more constants, and you're going to need something called an initial condition. What happens at time equals 0? So first, let's outline a problem for this. Let's outline a problem, which is essentially, let's say that we have some block, right? We have some sort of block, right? That looks like this. And outside, it's the concentration of the solute is C1 naught. But inside at, kind of infinity, let's say this block is semi-infinite, we're going to have a concentration of C1 infinity, right? Let's say that it has a concentration of C1 infinity. Important also to note our coordinates, right? Coordinate axis. So let's say going this way is Z. You can imagine that the solute is basically going to travel from C1 naught to C1 infinity, right? Let's say that C1 naught is significantly greater than C1 infinity, and so you're gonna need to you're gonna see mass moving this way into the block. And so the goal of this is, once again, right, the goal, calculate the concentration profile as well as the flux. Or actually, yeah, the mass transfer rate. Let's do mass transfer rate this time. So you want to figure out the mass transfer rate and the concentration profile. And remember, the mass transfer rate, when people ask you for the mass transfer rate, I'm wording it like this, but what that means is flux, right? So just this is another way to say flux. Perfect. And let's say that this time we know that at, let's outline our boundary conditions and our initial conditions. Let's say that at time equals t, at time equals 0, right? At t equals 0, the concentration throughout the block is always C1 infinity, right? Everywhere across the block, right at the beginning of time, it's C1 infinity. Another way this might be worded is before the block is placed in a solution, the concentration is uniform. And so what that would imply is that the concentration is C1 infinity, right? And so C1 equals C1 infinity. And this means that all z's. And then let's also outline our other conditions. So at z equals 0, right? Let's say the block is just then placed at at z equals 0, time has started. That means that this surface, right, as soon as we place the block, it's in contact with this surface, which is at C1 naught. So we can safely assume that as soon as we drop the block into this solution that has a concentration of C1 naught, at z equals 0, which is right here, this concentration on the block will also be C1 naught, right? So we can say at z equals 0, C1 equals C1 naught. Perfect. But I did say that this is a semi-infinite block, and so what that means is that yes, that z equals 0, the concentration will be C1 naught, but if we were to look at concentration profiles, it would look something like this, right, as time goes on. And so what that means is if I was to extend this block out, right, all the way to out here, it's kind of negligible, the concentration, once you get to a certain extent, right? Once you get to a certain z. And so what that means is that when you have an infinite block or a semi-infinite block, what they're typically trying to say is that as z approaches infinity, C1 equals C1 infinity. Right? Sometimes that might be also 0. Whatever it is, it's trying to approach the initial concentration. That's the point of the semi-infinite block. Perfect. Okay, so now we have to go back to our main equation, right? And you might notice, well, this is now we're back to Cartesian coordinates. And so what that means is that when we write Fick's second law, right? Fick's second law, which is dc1 by dt is equivalent to d dc1 squared by dz squared. We no longer need to worry about the Laplacian for cylindrical or spherical coordinates. This is the Cartesian Laplacian for where it's moving because it's diffusing across the z-axis. Perfect. And so now that we have this, you're going to realize that before, what we used to do is that we used to be able to cancel out this term, right? We used to be able to cancel out this term because it was steady state. In this case, it's not steady state. How do you know that it's not steady state? Because we're saying that the concentration profile is going to change over time. Once you bring time in as a variable, that means that there's some sort of time variance, and so the concentration is not going to be constant. It's not steady state. And so now this problem becomes a lot harder. So typically when you don't have this being 0, the way how you can solve this is through something called a similarity solution. So you're going to need to use a similarity solution. Similarity solution. And what a similarity solution basically is it's kind of like an educated guess, right? It's a guess that, let's say that the concentration is a function of some other variable, right? So what we're going to say is, let's say C1, right, is a function of some random variable we're going to call psi, right? And we're going to give a guess for what psi is. So let's guess that psi equals z over 4 dt, right? And this seems outlandish. Like, okay, where did you get this guess from? But the thing is that as you do these problems, you'll see that there's some sort of only some types of functions that will allow you to basically solve these partial differential equations. And so you kind of need to know what the similarity is beforehand in order to solve this. Otherwise, it would be very iterative and difficult. But typically, you'll be given what this similarity function is equivalent to. And psi is basically a function of z and t. Okay, so now that we're given what psi is, right, we can now change this fixed second law into psi, and it will allow us to solve this equation better. And so using chain rule, what we can do is now we can rewrite this, right? We can rewrite this as dc1 by, d squared c1 by d psi squared. This is not bold enough. By d psi squared plus 2 psi dc1 by d psi equals 0, right? And so how did we get from there to there? Well, we use chain rule. So dc1 by dt is nothing but dc1 by d psi times d psi by dt. So let me write that out. So if you use chain rule, right, on this is nothing but dc1 by d psi times d psi by dt, right? And so if you were to take the partial derivative, actually these should be partial derivatives. But if you were to take the partial derivative of d psi with respect to t, you would figure out that, you know, it would look something like this. Same thing with this. So if you take the two partial derivatives, you can use chain rule on this and basically get to this differential equation. I'm not going to do out all the chain rule because it would take a while, and that's not the focus of this video. But definitely, if you want to prove it for yourself, you can go ahead and do that. Okay, perfect. And so now that we have this, right, the important thing is now we want to change our boundary conditions. Why do we need to change our boundary conditions? Well, if you look back at this, we don't have any mention of psi, right? There's no psi's here. So how can we possibly apply our boundary conditions if the variable that's in our boundary condition isn't present in the real differential equation? So we have to transform the boundary conditions. And so if you look at this, right, let's look at this first one, which is t equals 0, c1 equals c1 infinity. So if we apply t equals 0 right here, the denominator goes to 0, right? And so what that means, as t is 0, as t equals 0, psi is basically infinity, right? And so what that means is that as psi goes to infinity, c1 is c1 infinity, right? So once again, let's apply this initial condition: t equals 0, c1 equals c1 infinity. Remember, c1 is a function of psi. At t equals 0, psi is infinity. That means that as psi goes to infinity, c1 is c1 infinity. So we'll rewrite these boundary conditions now in terms of psi. So as psi goes to infinity, c1 equals c1 infinity. So let's do the same thing for z equals 0, right? If we do z equals 0, psi goes to 0. That means at psi equals 0, c1 is c1 naught. So psi goes to 0, c1 is c1 naught. And we can also do the same thing for this last one, but you'll see that if I apply z goes to infinity, psi goes to infinity, and psi going to infinity, that means c1 equals c1 infinity. So this last boundary condition is kind of repetitive in that sense, since it doesn't give us new information. So these are our two boundary conditions now, psi going to infinity and psi going to 0. Perfect. And so if you want to think of this, this is a normal, you know, second order, like normal coefficient differential equation. And so if you want to, we can solve this as basically saying that let's let y equals dc1 by d psi. And so what that means is now we have, this is just normal differential equations, solving methods. And so we get this, then you do dy, you can take basically the integral, if I was to, pull this on the, actually let me do that. So this is y prime equals minus 2 psi y, oh actually, sorry, mistake. Actually, no, yeah. So we do y prime equals minus 2 psi y, divide both sides by y, you get basically y prime is nothing but dy. So let me rewrite that as dy. dy by y equals minus 2 psi. Take the integral of both sides, right? 2 psi, sorry, there's supposed to be a d psi here. D psi, because y prime is dy by d psi. So then you get ln of y is equivalent to minus 2 psi squared by 2 plus constant a, we'll call that a. And so if I was to raise this right side to an exponent, what I get was e to the a is nothing but another constant, so we'll call that a as well, even though technically it's not the same constant. A times e to the minus, these twos cancel out, psi squared. Perfect. But remember that y is nothing but dc1 by d psi, so it's still a derivative. And so what we have to do is that this is now dc1 times a e to the, right, times d psi. So take another integral. You got c1 is equivalent to, also for this one we can apply the bounds. So c1 naught, right, to c1. And what you get is basically this, oh, this actually needs to go. Let me erase this. Oh, don't need that. What we get is that since now we're integrating from c1 naught to c1, we get c1 minus c1 naught is equivalent to, take the constant out, and what you get is e to the minus, sorry, balance for this, e to the minus psi squared d psi. And so you may or may not know this, but there's a function called the error function, erf. An erf of, let's say in this case it's psi. And that's defined, the error function is defined as 2 over pi 0 to psi e to the minus psi squared d psi. So it's defined as this. You might be asking, okay, why do we have a special designation for this function? Well, we just see it so often that it got its own name essentially. So this might be useful in other applications too. But you can recognize that this is the error function. And so just going forward, what this means is that we can lump this term into this a term, just call it a new constant. And so what that means is we get c1 minus c1 naught is equivalent to a error function of psi. This is what that means. All right. So now that we have that, the only thing left now is to basically plug in our boundary conditions. And so what was our boundary conditions? We had boundary conditions as psi goes to infinity, c1 equals c1 infinity. As psi goes to 0, c1 equals c1 naught. So if we use the zero, the zero boundary condition, what we get is that, you know, 0 equals 0. And so this boundary condition, the second one, isn't useful for us. What is useful though is this one. If we apply psi goes to infinity, c1 equals c1 infinity, the error function as psi goes to infinity, here, this is something useful. So error function of 0 equals 0. The error function of infinity is equal to 1, and the error function of negative infinity is negative 1. If you want to see what it looks like, it kind of looks something like this, the error function. All right, that's very bad actually. But you get the point, right? Like it's 1 and minus 1, and here it's 0. And so what that means is that if we were to plug in the first boundary condition, error function at infinity, that's 1. 1 times a is a. c1 would be c1 infinity, and so what that means is c1 infinity minus c1 naught is equivalent to a, and that's our constant. And so now we can find what the concentration profile is. The concentration profile is nothing but I'll divide both sides by a, right? So we get c1 minus c1 naught divided by c1 infinity minus c1 naught. Right, if I divided both sides by a, and that's equivalent to the error function. I'm gonna go ahead and plug in what psi is. Remember, psi was z over root 4 dt, right? And so what we get is the error function z over square root of 4 dt. Perfect. And so this is our concentration profile. What does it look like? Well, if I was to redraw the block, right? So our block looks something like this. As intuition, what it would look like is this. So you have some C1 naught here, right? As time increases, this is what these curves would look like as some sort of intuition. Okay, so now that we have our concentration profile, we were also asked to find the mass transfer rate. And as I said earlier, the mass transfer rate is nothing but the flux. And so what's left to find is the flux. So as I said before, now that we have the concentration profile, how do we find the flux? Fick's first law. So J equals minus D. This time it's actually a partial derivative because then we have concentration changing with time. And so dc1 by dz. If you were to take the, I'll go through this actually. If you were to take the partial derivative, it would look something like this. You have c1 naught plus c1 plus c1 infinity minus c1 naught times the error function. I'm just going to denote it. Perfect. And so the constants basically come out, and what you get is that minus d times c1 infinity minus c1 naught times the derivative times the error function. This looks awkward. Need to separate the d, the derivative, from the error function. Times obviously d psi by dz. So what I did here was chain rule again, because d, the derivative of the error function by dz is nothing but the derivative of the error function by psi times d psi by dz. You can think of these as fractions. If I was to cancel out the d psi, it would still be the same derivative, right? If I was to, take it normally. But this makes it a lot easier since we have what psi is, and I can take the partial derivative of psi with respect to z. And so what that equals is derivative times c1 naught minus c1 infinity. You might be asking, okay, well, you swapped it around. I just didn't want this negative, so I took the negative inside the parentheses. Times, remember the air function was defined as 2 over pi integral of e to the minus whatever it is, psi squared d psi. So if I take the derivative of it, basically what that's saying is that this integral is, the integral goes away. And so what that means is that we have a 2 over pi term, right? 2 over pi times e to the minus psi squared. And that if you were to take the partial derivative of psi with respect to z, you would get 4 dt, right? Because going back to what psi is this. Psi is this, so you can treat everything underneath here as a constant. And so you just get the constant as the coefficient. Perfect. And so the square root of 4, right, that's 2. So this cancels out with this. I should do that in a different color. So this cancels out with this. And basically what you get is that j equals square root of d by 4, not 4, by pi t times e to the minus z squared divided by 4 dt times c1 naught minus c1 infinity. So this is your flux now. All right. So basically today what we covered was how to solve, unsteady state problems, right? So now that we have this not going to zero, how do we solve it? A similarity solution is the best way to go. Typically, most of the similarity functions will follow similar format like this, z over square root of some coefficient times dt. But essentially what you're going to do is that you're going to use that similarity function in order to integrate the PDE and basically get the constants. You might see an error function along the way. Error function is once again defined as 2 over pi, root pi times this integral. And so that's how you solve a non-steady state problem. If you were to solve a steady state problem in a different coordinate axis, you basically follow the same rules, except now you want to swap out the Laplacian depending on what coordinate system you're using. I just did a problem in cylindrical, and what that means is you basically swap out the Cartesian coordinate system for the cylindrical one. And that's basically some problems on how to solve some mass transfer. And hopefully in the next one, we can go over convection. Since all these problems basically had only diffusion as the mechanism for mass transfer. But as you can see, that doesn't tell you the whole picture, since diffusion can also cause bulk transport, and we will see convection also plays a big role. But that's it for now.